Welcome to this video on ethical hacking. Now, we're almost done with some of the foundational work here, and we're going to be getting into some actual hacking and the methods shortly. But for this video, we need to talk about some foundational knowledge in networking, and we're going to go very, very basic here. If you don't understand what we're talking about in this video, I recommend going through the Network Plus series that I have posted as well, where you will cover over several hours all of the facets of networking. To be a good ethical hacker, you really have to understand your networking foundations, because we are going to manipulate packets, we're going to capture packets, and we're going to change the way that they are used to produce effects that we want as we go through this course. So you really have to understand the theory behind it, and then we're going to do the practical application of it as we move forward. So with networking, there's two different reference models out there. One is called the Open Systems Interconnection model, and you see that listed on the left side of the screen. We also have the TCP stack or DoD model, and we'll get to that one shortly. What a reference model does is it describes the flow of communications in a networking environment. So this serves as a common point of reference for how a particular technology fits in. Now, this isn't necessarily practical application by talking about OSI. Not all things clearly fit into one of these 7 layers, but it does help you have a good understanding of how things flow through the layers as we communicate from one machine to another, or from an attack machine to a victim machine. This gives us a common reference as we compare technologies across manufacturers, as well as to talk about the data flow paths. So we're going to start with going through the OSI model, and then we're going to talk about the TCP/IP or DoD model stack. So the first layer of the OSI model is the physical layer. So we're going to start from the ground up. When we talk about the physical layer, we're talking about how our transmission of bits accomplished. So this is your physical and electrical characteristics. For example, if I have a cell phone and I'm using cellular signals as my network connection because I'm using my iPhone, that is using a radio frequency to transmit the zeros and ones. Converse that with my laptop that's plugged in through a network cable, I'm using electrical pulses of zeros and ones over a cable. So things that we would talk about in the physical layer is our cables, our hubs, our repeaters, and radio frequency devices like Wi-Fi and cellular. We're talking about how the bits are represented on the median, how the wiring is done for jacks and connectors, the physical topology, how we synchronize, how we utilize our bandwidth, and any multiplexing strategies that we talked about. So this is just a very generic talk about the layer 1, physical layer of the network. Then we're going to move up to layer 2, which is our data link layer. Data link is concerned with packaging data into what we call frames. Ethernet runs off of frames, and we transmit those frames on the network, performing error detection and correction, and uniquely identifying network devices with an address called a MAC address. And we use flow control here too, so we can know when things need to start and stop. Examples of layer 2 devices are things like switches, bridges, network cards, and MAC addresses. And we'll talk a little more about MAC addresses in a later slide. As you can see in the diagram, we have the data link. It has the MAC addresses, which is your physical addressing, your logical topology, and your method of transmitting on the media. Your LLC, your link layer control, is used for that flow control. So we're doing our connection services and synchronizing our transmissions. As we move up the stack, we're going to get to layer 3, the network layer. The network layer is what we concern with forwarding traffic, also known as routing, based on logical addresses. So when we talk about physical addresses, we're talking about layer 2 MACs. When we talk about logical addresses, we're talking about layer 3 IP. And that could be things like IP version 4, IP version 6, some old school IPX connections, and we do this usually with a router or a layer 3 switch. In the network layer, we have logical addressing, we have switching and routing discovery and selection, connection services, bandwidth utilization, and again, multiplexing strategies. As we move up the layers, we go up to layer 4, the transport layer. This is the dividing line between the upper and lower layers. As you can see, it's right in the middle of the diagram, and data here is sent as segments. And with these segments, we can actually go ahead and we can take our data, chop it into chunks, and send it out. So we can do things like TCP, UDP, or ICMP, which are different connection protocols that we would use in this. If we're using TCP, for instance, we do windowing and buffering to make sure the data actually gets where it's going to go. And we'll talk a little more about TCP and UDP in later on. But again, if you don't understand some of these foundational concepts, please go and check out my Network Plus series. We go into all these in much more depth. And I'm assuming at this point you already understand that if you're studying for the ethical hacker exam. Layer 5, the session layer. So we want to think about a session like a conversation that has to be kept separate from others to prevent intermingling of data. For instance, if I'm talking to my wife on the phone and I also want to talk to my friend, I would have to make 2 separate calls, otherwise we'd all be able to hear the same conversations. So I want to keep those flows of traffic separate. In a session, we're concerned with setting up, maintaining, and tearing down a session. So I might start a session by going, hey, honey, I want to talk to you. We start talking, and at the end I say, okay, I'm done, goodbye. Right? That's setting up, maintaining, and tearing down a session. We do this with many different protocols. Some examples would be NetBIOS, H323, which we use for video and audio, and many other ones out there. Again, for this exam, you don't need to know all of those session layer type protocols. If you're doing Network Plus or CCNA, you're going to be needing to know that. And it's assumed knowledge at this point in your career if you're doing ethical hacking. Layer 6 is the presentation layer, and it's responsible for formatting the data that's being exchanged and securing that data with proper encryption. So for example, if I have a text file and it's in ASCII code, I can read it as text. The computer understands it as ASCII numbers. That's data formatting. Same thing with a GIF. GIF. Now I got people got me saying it. A GIF or a JPEG file or HTML files. When we start getting to SSL and TLS, we start talking about secure socket layer and transport layer security. This is encryption, and encryption is also handled at the presentation layer. So it's the way we format the data or the way we encrypt the data is all handled at this layer 6 presentation layer in the OSI model. And finally, that brings us up to layer 7. Layer 7 is focused on the application level services and service advisement. Now, when I talk about application level services, I'm not talking about Notepad or Word or Internet Explorer, but instead I'm talking about server applications like DNS, domain name service, Telnet, FTP, POP3, IMAP. Why would an ethical hacker care about these type of services? Because all of these services have vulnerabilities that I can exploit to my advantage as I start working on it. And for that matter, there's exploits for all of these layers as we go through. For instance, we talk about the network layer and we have IP addresses. I can spoof IPs. If there is MAC filtering on the network to protect it so that only this certain MAC address on a laptop can get there, I can spoof that MAC and I can get on the network. And that's a data link layer attack. So there's all sorts of different things that we can do as we go through. And if you understand the way networks work, you can figure out where those holes are and where you can exploit them. So the second model we mentioned was the TCP/IP protocol stack, also known as the DoD model. In this model, it's a lot simpler. There's only 4 layers. You have the network interface, the internet, the transport, and the application. Sometimes this is also referred to as the network access, internet, host to host instead of transport, and then application. This is the standard for IP networks. That's why it's called the TCP/IP protocol stack. Now, the OSI model refers to all networking across any type of protocol, whereas TCP/IP is focused specifically on the way TCP/IP works. Now, the good thing about that is we use TCP/IP for pretty much everything nowadays, and so it's a very good model for us to use. It contains multiple protocols, but the 4 main ones that we talk about are TCP, IP, UDP, and ICMP. Now again, we talked about those briefly in the OSI model. Here we talk about them again, but these are the ones that we really focus on for the TCP/IP model. So if you want to look at the way the stacks line up, you can notice that the bottom 2 layers, the data link and physical from the OSI, are lumped together to call it the network interface on the TCP/IP stack. Network became internet, transport stays as transport, and then application, presentation, and session all combined into that top layer of application. That's how we go from 7 to 4. They're doing the same stuff, we just sometimes bundle them together differently. So, network access layer. This is responsible for physical delivery of IP packets. So this is the old layer 1, layer 2 of the OSI model. We use Ethernet frames using MAC addresses for identification. We mentioned that in layer 2 of the OSI model. And those physical addresses are going to uniquely identify a particular NIC, or network interface card. This could be unicast traffic, multicast traffic, or broadcast traffic. If you see 12 Fs in a row, that's a broadcast message. It's going to go to everyone on that network segment. Otherwise, you're going to have a unique 12-character code written in hexadecimal that identifies your network device, your MAC address of that device. And every device out there has a unique MAC address. So we can use this in security by having our switches and routers only allow those particular MAC addressed devices onto our network. The problem with that is, as an ethical hacker, from a bad guy perspective, I can make my laptop's card respond that it has any MAC address I want, not just the one that's physically burned into the card. So if I know that your MAC address is allowed on the network and mine isn't, I'll just change mine to yours and use it. And that way I can spoof the MAC address and get on the network. We'll talk about that and we'll actually demonstrate that in later videos. So another thing in the network access layer we have is a thing called ARP, Address Resolution Protocol, and this is used at this layer as well. It converts our IP addresses to MAC addresses. So with ARP, there's a two-step process. There's a request and there's a reply. So as you can see in the diagram there, the source computer requests it, it goes to the switch goes, I don't know who that is that you're asking for. In this case, the target of 192.168.0.1. So it asks, hey, does anybody know who that is? And the guy who it is says, yep, that's me, and my MAC address is this, and responds that back to the requesting computer. And then in the local network, they talk based on MAC addresses. With ARP, there's a lot of attacks that we can go after it, and we'll talk about them and show them in later videos. We have things like man-in-the-middle, spoofing, session hijacking, and ARP table poisoning, and I'll just demonstrate those in other videos for you to watch and follow along with. The internet layer. The internet layer is our second layer of the DoD model or the TCP/IP model. It contains the following protocols. It contains IP, ICMP, and ARP. For IP, it provides our source and destination addressing. It's responsible for our datagram fragmentation, so we can actually fragment our packets as we're sending them across, and it's routable over the internet. Internet Control Message Protocol actually is a series of control and error messages, and when you do a ping or a trace route, you're really using ICMP. We'll use that a lot in this as we go through, and we'll actually, for the ethical hacking exam, you're going to have to learn the codes associated with ICMP, such as a code 8. Address Resolution Protocol, ARP, we talked about it before. It takes your IP addresses and converts them to MAC. If you have RARP, it stands for Reverse Address Resolution Protocol, and that takes your MAC addresses and makes them into IPs. Both happen on the network all day long as you're doing stuff on the network. So if you have an IPv4 address, if you don't know your IP scopes, you got to learn those. You got to know it's public and you got to know it's private. In the bottom of this chart, you'll see the private scopes, the 10 addresses, 10.x.x.x for class A's, the 172.16.something.something to 172.31.something.something that makes up our class B, and our 192.168.something.something that makes up our class C. Those are your private addresses. You got to memorize those. They're going to come up on the exam over and over again. Up in the top, you'll see there's class A, B, C, and D. Again, when we get into D, we're talking about multicast addresses. When we're talking about E, we're talking about restricted and experimental. You got to understand where those ranges start and stop. A, 1 to 127, B, 128 to 191, C, 192 to 223. If you understand this page, again, this is Network Plus knowledge and A Plus knowledge. You're expected to know that going into the CEH exam, and you really just need to know it as you start working in computers in general to know where things are and what scopes they're going to be in. The reason why this is important, let's say I took a scope, a /8, right? I had a 10.something.something.something address, I use a /8, and I do a ping sweep. How many hosts did I just look at? 16.7 million hosts. Probably a little bit outside the bounds of my scope. I got to be careful about that. So you need to use the right subnetting and the right prefixes to actually get what you want. Packet fragmentation. I mentioned this a little bit earlier, but at the internet layer, we can actually fragment our packets. So if our network can only handle packets that are of a certain size, we might have to break them up into smaller chunks. So I can send it as a 1500 byte packet. What if my routers only accept 1000? Well, then I have to break up into 1000 and a 500. What if they only accept 600? Well, then I'll do 600, 400, and 500. And it can break those pieces apart. This is all determined based on your maximum transmission unit size. MTUs are configured on the routers and switches. Generally, 1500 is a standard number of bytes. So usually that's what you'll see. Modern networks should have little fragmentation. Fragmentation is an indication usually of malicious intent. One of the techniques that bad guys can use is they can actually chop their packets into fragmented pieces, push the fragments through your sensors, and then put them back together. This actually first originated way back in the day in Windows 2000 and Windows NT systems, and it was called a teardrop attack, where they would basically send fragmented packets over, and if they overlapped and the system couldn't put them back together properly, like you could see in the third line there of my drawing, the 600, 400, 500, it would cause the system to actually crash. The ping of death. Ping of death uses fragmentation as well, at a total field length that IPv4 can't handle, and it crashes the host. Again, in recent years, the ping of death and the teardrop attack have been solved by the operating system, but there's other techs out there that use this fragmentation as well, and we'll talk about those as we move through in the future and demonstrate some of those. The other thing that's really good with fragmentation from an attack perspective is if you have a sensor like an IDS or an IPS, and it's looking for known bad packet that's 1480 bytes, if I fragment it into half and it sends out 700 plus another 780 bytes, it might go through the sensor without being caught, because you can fragment it out so it doesn't get seen. Most sensors are getting smarter, and they're starting to put those packets together and analyze them as a full piece, and not let the fragments through to the host until they look at it. But again, depending on what your customer has, it may be something that's a useful technique for you. The transport layer, layer 3 of the TCP IP model. The TCP stands for Transmission Control Protocol. It transports data from one host to another, and we call this our connection-oriented protocol because it is there for reliable delivery. It performs a 3-step handshake. So with TCP, I'm going to say, "Hi there, target." The target's going to answer back, "Hi there, source." And then I'm going to answer back and say, "Hey, I know we're talking," and then we start talking. So we do this 3-way handshake, and I'll show you what that looks like in a second. And once we have that 3-way handshake, I start sending data. So say I send 1,000 pages over, then the destination goes, "I received 999 pages. I'm missing page 38. I go, "Oh, okay, let me send you that again." And I send it to him again to verify he got it. UDP, on the other hand, is the fire and forget method. It's very fast because there's no guarantee of delivery. It has a lot less overhead. There's no handshake, and it's called a connectionless protocol. There's no connection. So with UDP, I usually use this for streaming audio and streaming video. I just fire and forget. If I threw you 100 seconds of a song and you only got 93 of them, you're going to play the 93 you got. You're going to have skipping and buffering happening because you don't know that you dropped things. If you're using a voice over IP, you'll see this a lot. Voice over IP systems use UDP, which is good because it gives them fast delivery of the packets, but there's no guarantee. So if I'm talking and you start hearing ooh, ah, in the middle of your calls, or you're dropping parts of the audio, that's usually an issue with the UDP and this quality of service. So when I talk about that 3-way handshake, TCP uses things like SYN and ACK to do that 3-way handshake. SYN is for synchronize, ACK is for acknowledge. So SYN, "Hi there server, I'm the PC." SYN ACK, "Hi there PC, I'm the server." ACK, "I'm the PC, hi server, let's talk." Once we do that 3-way handshake, we start talking. When we're done, we're going to shut down our connection. I'm going to send a FIN-ACK. They're going to acknowledge my FIN-ACK, send me a FIN-ACK, and then I'm going to send them back an ACK. Okay? You have to know this 3-step up and 4-step shutdown. The other thing you need to be concerned about is things like push, reset, and urge. Later on, we'll play with Wireshark and we'll actually start looking at packets, and you'll see these little flags are going to be flipped. There's different scans that we use out there. Null scans have no flag set. Christmas tree scans have all those flags set, the SYN, the urge, and the push. Port scanners, things like Nmap and Zenmap, they're going to tweak which flags they're going to use to be able to perform scans either more or less stealthy. Okay? There's different ways of doing it, and we'll talk about those as we start getting into the practical nature of it, but you got to understand that the TCP has these different flags, and we're manipulating those flags to cause a desired result. The application layer, the last layer of the DoD model, or the TCP IP model. It's responsible for application support. Applications are mapped by port numbers, not names. So, why are port numbers important? Because ports are the open holes on a computer and open holes on a firewall. So if you're running an FTP server on your laptop, that means you have port 21 open. If you have port 21 open for legitimate traffic, I can also use that as a method of getting in there, right? So if I'm going after a web server, I would expect that to be port 80, HTTP. Or if it's a secure web server, port 443, HTTPS. You got to understand your ports and your numbers. You're going to see questions on the test for it, and just in practical knowledge, you have to know what they are. So if I see something like 69, I know it's TFTP. If it's DNS, I know it's 53. 25, SMTP, things like that. Any port that is under 1023 are what are defined as well-known ports. Okay, so 1 through 1023 are the well-known ports. Ports from 1024 to 64K, 65,535 are what we call ephemeral ports. Remember those two terms, well-known versus ephemeral. Ephemeral ports mean we don't have them assigned to any particular traffic as a well-known port through an RFC process, and anyone can use them. So when your web browser goes to my website, You pick a random high port on your website from your web browser. My website is on port 80, and I answer back to you on that ephemeral port that you chose. Common ports and services must be known by ethical hackers, okay? You have to know them. And to make it easy for you, I've created a little chart. These are the ones that I would definitely memorize for the exam. FTP, Secure Shell, Telnet, Simple Mail Transfer Protocol, Domain Name Service, Trivial File Transfer Protocol, Hypertext Transfer Protocol, Remote Procedure Call, NetBIOS Sessions, Simple Network Management Protocol, Hypertext Transfer Protocol Secure, Server Message Block, and Remote Desktop Protocol. If you need to, take a screenshot of this, write them down, memorize them. If you're taking the CEH exam, you got to know these ports up and down. If you're taking Security Plus, you got to know these ports up and down. Every IT exam you ever take, you're going to have to memorize ports, so just get used to it and go ahead. It also helps when you're doing your attacks. You got to know where things are and know what things that you're looking at. So if I do a port scan of a machine and it comes back and says, hey, I've got port 135, 139, and 445 open, well, to me, that tells me that they're running SMB, which is Windows file sharing. So now I know that I can start looking at attacks that focus on Windows machines. And I can actually look based on what the response I'm getting from those, and I can actually identify if it's a Windows XP box, a Windows 7 box, a Windows 10 box, because each version of Windows handles the response to those queries a little bit different. And we'll talk about that when we go into the practical and deal with Nmap, which is our network scanning protocol that we're going to use, network scanning program that we're going to use, network map, Nmap. And we'll talk about that in a future lesson as well. But you got to memorize those ports and protocols. That's it for this lesson. That was a very quick, very brief overview of TCP, IP, and OSI models, the foundations of networking. Again, I'm not going to cover all the networking topics again. I have an entire series of Network Plus videos. If you need to, please go and view those. They're there for you. And we'll go into all the depth you need to get you that network background. But I'm going to assume you have that background as we move forward in this course and we go forward in ethical hacking. If you enjoyed that video, please subscribe to our channel.